Hi, welcome to the MPI workshop presented by the NSS Exceed program. This was originally a 2-day event with hands-on exercises that you can view at your own pace.
I am going to jump into Outro to Parallel Computing, which is where we can talk about some of the more software related issues, both with MPI and alternatives to MPI, because so far I've kind of more than implied, I've explicitly said multiple times now, MPI is the way you program these large machines. But let's look at some other alternatives that may or may not work on large machines, but certainly the domain of parallel computing, so you may or may not interface with them. And so before we do that, one of the things you want to do is kind of define how well the technique is working, either your MPI code or some alternative you might have. And it turns out that there is a fairly universal metric that's pretty good at quantifying how well you're doing as a parallel programmer, and that's the scalability of your code. How well does your code scale up to larger numbers of cores? And this is the question that you should ask of anybody that claims to be have a great parallel program, or be a great parallel programmer, or have a great algorithm, or have a package that's parallel. It's always important to ask what the scalability of the project looks like, or the application looks like, to know if somebody really understands what they're doing with scalability, or what the benefits are ultimately going to be by running on some multi-million-dollar machine. And the scalability graph is very simple. It just shows you your speed up versus the number of processes that you're running. And that gives you a good indication of, well, for one thing, whether it's worthwhile running at very large scale. This particular graph in front of us right here, we can see that, running on 1,000 processors gets us a nice speed up. We're over 500 times as fast, so it's worthwhile. We certainly can do a lot of science maybe we couldn't do otherwise, but running on 10,000 processors isn't going to do anything other than waste processing cycles. We've hit this asymptote here. So scalability is a simple but direct metric to allow you to figure out, again, how well the application is, how good the programmer is, how good a paradigm that they're suggesting that you use is. And that's maybe the most important thing for those of you that think that there might be an alternative to MPI that I'd be interested in looking into because some computer science guy told me about it. And you can say, okay, show me some scalability graphs or some successful applications using this approach. And that ultimately, that's the reality check. There are a couple kinds of scalability, though. There are two kinds of scalability that can be mentioned: strong scalability and weak scalability. And they don't let the names prejudice you into thinking one's more valid than the other. They each have their domain of usefulness. Weak scaling is where you take and run the problem on more processes, not to speed up, but instead to be able to run a better problem, get a finer resolution in the case of our weather map, for example, get more accurate results. So when you do weak scaling, you're changing the problem as you throw it on more processors. That's as opposed to strong scaling, which is where we keep the exact same problem as we run on more processors. And so strong scaling would give us an indication of taking the same problem we could run potentially in serial on a single laptop, but now we're running it on 1,000 processors or 10,000 on a supercomputer. How much faster does it run? And that can be, in the weather domain, that can be equally applicable. If we're doing tornado modeling, for example, our main concern might be that our tornado prediction is very accurate, but it took 8 hours to tell us a tornado is going to strike in 30 minutes. That's not real useful to us, right? But if instead we can run that on a supercomputer, and so our simulation now takes 2 minutes to run and tell us a tornado is going to hit in 30 minutes, that's really valuable, right? So strong scaling runs, basically you can think the same problem but faster. Weak scaling allows us to attack a different problem as we scale up. And they both can be applicable, but you do want to ask which one you're looking at when somebody is showing you or discussing scalability to make sure it's the kind of problem that interests you with that application. Your enemy in scaling is very often something called Amdahls Law. And you may even have heard the term before because it's bandied about quite frequently by people who don't really appreciate its applicability or how afraid they should be of it. When I first got involved in parallel computing, and it was a very immature field at that point in time. There were a lot fewer success stories, and so people would frequently tell me when I said, hey, we should really consider parallelizing your application, people would say, well, Amdahls Law just tells me it's just not worthwhile. Ultimately, it's not going to pan out. Let's look what Amdahls Law is first. Amdahls Law basically says that the portion of code that you can't parallelize is going to limit how successfully you can scale up. Let's look at a case where we've got a code that runs for 100 seconds of time. And if we break down the runtime of that code, we find there's one subroutine in there that takes 50 seconds of time. A lot of the number crunching happens in there, and we can parallelize that routine very successfully. But these other routines here, we can't really see a way to break them down well, and so I'll give you maybe a cliche case. Maybe this is I/O. It takes us long to read a disk file and then to write it out. There's nothing we can do about it, so we speed up the math part of the code a whole lot. Well, what happens if we run this code on a larger machine? If we run this on 5 processors, say on your laptop, we run it across 5 processors, and we find it speeds up by almost 2 times, right? Because the portion of the code that's parallelized speeds up nicely by a factor of 5. The I/O part's still sitting there bogging us down. But, hey, that's worthwhile. On your laptop now, you've got the code running at half the time it used to take. Maybe now you can do a lot more work in the course of the day. That you might consider that a win. On the other hand, let's say we put this on some big expensive cluster you've got with 1,000 processors, and we run it there. Well, the part that we parallelize speeds up. It takes just a fraction of a second, but the parts that don't speed up still take 50 seconds. We've still only sped it up by about a factor of 2, and now we're running on a lot more expensive hardware, and you go, okay, this isn't that much of a win. So Amdahls Law has caught us and shown us that it wasn't really that worth parallelizing this code to run on a big machine because it's not going to speed up that much. Now, this is the math of this, you can see, is very, very straightforward. It's just simple algebra to say what percentage of the code that we have that's not parallelizable or we haven't parallelized. And that's going to limit how large we can really run this thing effectively. So here's an example of some codes, very fractions of codes here, versus how much we can expect them to speed up. So if our code's only been parallelized, so it's half of it's running in parallel and faster, no point in running on much more than, say, 8 processors. That's not very many. On the other hand, if we parallelize 99% of it, we can see we can expect good results up to almost 1,000 processors. We can get some nice speed ups, and it's worth running on. And this is Amdahls Law right here in a very mathematically harsh form that shows us that there's no point in, say, trying to write massively scalable code that's going to run on 10,000 processors or 100,000 processors because surely at least a couple percent of our code is going to be hard to parallelize, blah blah blah, right? And this is the argument that I used to have to overcome back before there were a lot of success stories. Now today, the counter-argument, and people still like to invoke Amdahls Law when they're afraid of parallel programming. Today the counter-argument is simply that there are countless codes out there in the literature in all different domains of science that clearly run on tens of thousands of cores very successfully and scale well, if not more. So clearly it is entirely possible to write codes that have no significant fraction of them that are serial. And that is now an empirical fact. This isn't my guess, or maybe we can cross our fingers and hope to be pioneers. You can find, again, across many domains of science, codes running on these big machines that scale very well because they don't have even 1% of the code that's inherently serial. So that's now a given. It's not worth arguing about because we can find countless literature reinforcing that fact. So you can take it with a little bit of credibility here that yes, you should expect to write your codes with MPI so that almost the entire run is entirely in parallel, and you should not resign yourself to saying there's just these inevitable serial things in the world and we can't get around them. Again, the data refutes that. No longer big debates with me, but that's what Amdahls Law is. So don't let somebody scare you with Amdahls Law when you're taking your code, suggesting you parallelize it. Say, well, Amdahls Law is going to sting you. It's inevitable. This is what it is. You should be concerned about it. You should not be cavalier about letting pieces of your code remain serial because they will catch you if you have any ambitions of scaling up to big machines these days. But the reality is that this barrier has been overcome again in many different areas. So you're going to write some scalable code. You know MPI now to some degree. You may know some other things. Surely you'll stumble across friends who have other recommendations or other knowledge. So the first thing you need to do when you write your scalable code, you got to pick your language or maybe your paradigm, whatever that happens to mean in any given context. So you're going to pick one. And parallel programming options are countless. This is a slide I haven't updated in many years because there's no point in updating an endlessly revolving list of failed methods of doing parallel computing. There are people constantly coming up with ways to well, in many senses, to avoid doing MPI. There are a lot of people that are saying MPI just is too much effort, and there are languages that will give you it for free, that will just magically make parallelization easy. Countless list of them, but recognize that for all the many options that you can put on any given list of parallel computing languages, the vast majority of them are defunct and gone, dead, and took a lot of supporters' efforts with them. So you commit to one of these experimental approaches, you're taking a risk that your efforts are going to be wasted. Is probably not an understatement, because I've dealt with more than a few projects where their commitment to something that lost support and went away and died took down all of their existing code with it. So you don't focus on that. Instead, say, what's the appropriate general approach? This is where paradigm comes into play to breaking your code down. Should it be message passing, like we've been doing here with MPI? Because there are some other approaches that do actually have workable existing languages to support them, that do have success and do have momentum, and will probably be around for some time to come. Let's look at those quickly in comparison. With MPI, I went through this list yesterday of the pros and why we should do it. I won't reiterate that. The cons I kind of glossed over, but now maybe we can approach this list with a little bit more knowledge here. The lower level does mean we have to worry about things line by line. If you're in the midst of doing the Laplace code right now, you are worrying about indices. Am I passing the right row or column? You're having to worry about some detail. It's not novel to programming, but it's not fun either. Debugging. So far, I haven't given you the benefit of any serious debugging tools. I'll show you the wonderful options that are available in a few minutes, actually, but we haven't covered that yet. And so debugging so far can be a little bit frustrating. I'm sure so far you've had a code that's hung, just sat there because some message blocked and it just hung. You probably stuck some print statements in your code to try to get a handle on things. Debugging parallel code, MPI type code, does require a different mindset. Multiple things are going on simultaneously. The opportunities, for bugs to happen are different and numerous. So that's not a plus. The domain decomposition that we've had to do here, was something that we had to explicitly jump into our code and add to it. We had to take our metal plate and break it up into pieces. You'll have to take your molecule and figure out how to split it up in space, if that's your thing. You have to take your cosmos and figure out how to break up the stars that are out there and the galaxies that are out there into pieces in ways that that work efficiency-wise. Adding that into your code, that's not a bonus either. So it takes time to do an MPI port. It takes time and it takes effort. It's not the kind of thing you can do in an afternoon like you might hope with, say, OpenMP. With OpenMP workshop, for example, we kind of, I don't think we mislead people into saying, hey, you can go back and throw this at your code this afternoon and hope to have some success. And it's true. With OpenMP, we can throw some directives at a loop and get some substantial gains in an afternoon. Limitation of that is that we'll never scale off of the single workstation or laptop that they're on, but they can have, great results in an afternoon. That's not the case with MPI, right? It takes an investment. So this idea that we have to really start from scratch and work on our code from line 1 down to the last line, that's not a plus. So these are the cons. So let's look at some attempts. Well, these aren't just attempts. These are things that actually exist that people use successfully that aren't MPI. Data parallel is undoubtedly the most common in that it exists just as the way people do Fortran 90 code. So if you're a Fortran programmer, again, I hope, sadly it's not always the case, that you default to at least Fortran 90 syntax to do array operations, because why wouldn't you? All parallel programming aside, isn't it nice to just say A equals 2 if A is an array, just to initialize the array equal to 2? Why wouldn't you do that? So data parallel has been part of Fortran for a long time. It's now been absorbed into a lot of other languages, try to take this approach and to varying degrees and use it. It's, for example, the basis of kind of the NumPy approach used in Python. C++ hopes to adopt some of these things. So array shaping and slicing and all the things you have in Fortran 90 are just a wonderful way to write code. Forget the parallelization aspects. So happens that this stuff is almost automatically parallel. So here's an example. Let's say we have an array here that's 4 by 4. This is trivial, but a 4 by 4 array. We could set that array equal to 2 just by saying A equals 2, all the elements are equal to 2, for example. And we can do things like, say, C equals A plus B, where these are arrays. And what happens there is that if we have array A and B here with these elements, what happens is behind the scenes, the processors could work on this in parallel by having processor 0, say, add 2 and 2 to get 4. Processor 1 adds 3 and 2 to get 5. So this thing could be worked on by 16 threads in parallel with no effort on the programmer's part. It's completely, the runtime system does this in the background. And that's not an unreasonable expectation for Fortran 90 code using data parallel type statements. So data parallel is just saying, let's use array operations to express what we're doing, and then the parallelization opportunities are so obvious that the compiler and the runtime system do it automatically. I don't worry about anything. Data movement, that's computation. Communication behind the scenes is also expressed in these array type operations. For example, a shift operation, we take an array and say it's equal to a shift of another array B here. It's just sliding all the elements over in some particular direction by some amount, and that's communication that's happened. Data has been sent in the background behind the scenes, and it didn't require the programmer to do too much work right there. As a matter of fact, these things are often built on MPI. These compilers, all the real ones, are built on top of MPI. So behind the scenes, some MPI happened to send data between processors to make this happen. So data parallel is wonderfully straightforward, and it's so simple, you just learned the key elements of it right here if you've never used any data parallel statements before. Or if you're a Fortran programmer, who knew? You already knew data parallel programming. It's, of course, fairly easy to debug because it's line by line of code, not a lot to go wrong. So data parallel, why isn't all parallel programming done with data parallel if it's that simple? And the answer is that probably more programming should be done with data parallel that works on regular array structures like image processing, for example. I see opportunities where people do things like image processing, and they don't use data parallel approach or constructs, and it's silly because it would work great. On the other hand, in the real world, most problems are not so regular. Our Laplace code would be brilliant as a data parallel problem. It would be almost trivial to do our Laplace code as a data parallel problem. However, our square metal plate is probably not the ultimate goal of somebody writing a thermodynamics modeling package. They don't want to just work on a square grid. They do want to work on a turbine blade with its weird shape in an FEA case. In the real world, we don't have these regular array operations that represent everything, and as soon as you depart from these very regular array operations, you end up with ugly cases that don't have easy solutions or don't have any solution that's not going to just crush your performance. So data parallel is not the answer for anything that's irregular, and sadly, most of the world's interesting numerical work is not quite that regular. So it's wonderful, it has its place, but it's not the answer. What's a different approach that can deal with irregular things certainly is something like threading with OpenMP. OpenMP doesn't worry about breaking up our data into pieces. OpenMP worries about breaking up our loops into pieces. In other words, it takes a loop, a do or a for loop, and it uses these directive instructions, kind of hints to the compiler, and it can take and decompose this loop into a bunch of pieces that the different PEs will work on separately. And this does indeed work wonderfully well. And it's something that can be done to an existing code with sometimes an incredibly modest amount of effort. Here's a way that this particular code was put onto a GPU, threaded on a GPU with OpenACC, one directive, and it speeds it up by a factor of 100 and some, which is this. Didn't mess with the original serial code at all, just added a directive. Fantastic, works wonderfully. But it's limited to just a loop that's running on a single processor, maybe multiple cores on that processor. That's the real effectiveness of OpenMP, is that modern processors have a lot of cores in them by default, and so we can use those multiple cores, but that's as far as it can reach. It can't go past the processor. It can't combine things across multiple nodes. So if your ambitions are to work on a single processor or a GPU, then it is great, and it is easier than MPI. Not always, though. So CUDA, which is the predecessor to OpenACC, is some pretty ugly stuff. So if you're a GPU person and you look at a lot of the existing CUDA base of code, it might seem like it's inevitably got to descend into some low-level stuff like CUDA. That's not the case. OpenACC does allow you to do things at a much higher level. But again, it's still limited. So the things here we won't go into with threading and whatnot there are lots of other options as well. You may have, let's see where I have it. With Intel, for example, they've got, so even in the case of Intel's got so many options, it can be confusing at times. They've got threaded building blocks and Silk to do threading. Microsoft has AMP to do it. They also have direct compute. So there's so many different ways to do threading out there. It's confusing, and so we won't even go over the list. Options are many, but they're all limited again to working on a single processor. Python threads, one thing to be aware of is Python threads due to the global interpreter lock. Something, if any of you that use Python for performance purposes, I'm sure are familiar with the global interpreter lock. It stands in the way of most optimizations. So Python threads are not real threads. They can't run concurrently, but at least you can learn to program with threads with them, learn the techniques to apply elsewhere. But all of these are limited to a single processor. So that's really the reason that that people don't get excited about using threaded approaches that want to do large-scale, scalable numerical computing. Also, the serial code, it's neat that you can do one loop at a time, but if you are doing one loop at a time, then Amdahls Law does come back to be a very serious threat. With MPI, we're not worried about one section of our code or another. We're pretty much we're resigned to accelerating our entire code. With these threaded approaches, it's the nifty part of it is we can do one subroutine at a time, but then Amdahls Law really does come into the foreground. So there's many approaches there we could use. There are some more recent attempts. Well, they're not so recent anymore, as indicated by the fact it's part of the Fortran 2008 spec, and Fortran, Fortran, and UPC have been around at this point a long time. So they've had a while to prove their worth, but so you can make the argument that they're really not catching the world on fire. But at any rate, they are serious standards at least, and there are some existing compilers that attempt to use the best parts of MPI and the best parts of data parallel together. They say, okay, we like the fact that data parallel allows us to work with these array operations, but we acknowledge that in real applications, the irregularities make MPI much more flexible and able to deal with things. So let's have data parallel operations, but we'll have some things that can descend down to that per processor level and do individual manipulations of things there. And the PGAS languages the partition global address spaces. So the idea is we've got a global address space, so the arrays are spread out, but they're partitioned and we can work on things individually if we have to. So maybe that'll get us the best of both worlds, and that's the hope. These approaches have been around for a long time. So, Fortran was absorbed into Fortran 2008 standard. There aren't a lot of great implementations for it. In fact, I don't know of one full implementation of 2008. There are a lot of most partial implementations. And Unified Parallel CUPC has been around an equally long period of time. So they've been around a long time, the hope being that they'll combine this best of all worlds. But the reality is there just aren't a lot of success stories to point to. And at the end of the day, I try to be evidence-based on these things. And if something's been around for 20 years, doesn't have a whole lot of wins, you have to recognize that as part of its record, I guess. Something that also kind of disappointed me for a long time until recently, in terms of it being a viable approach to avoid you having to write all this MPI code but still get the benefits from it, is to use a framework where somebody else wrote most of that code for you and you just come and drop in your science. And indeed, Charm is an MPI framework, basically, where you drop in your science. There are, people that they've done all the effort to write these generic things we've talked about, like ghost zones and halo exchanges. I said this applies to a large class of problems. Well, hey, let somebody else write that code so that it's the same code applied to a large class of problems, and you'll come in and stick in that kernel, that in our case, our Jacobi solver in the middle, and let the framework take care of the rest. Furthermore, those people can do all the niftiest stuff, worrying about overlapping computation and communication and doing load balancing and everything else. Let them do all that work, and you come in and plug in the science. And this framework approach has been around for a while, but the only really successful example you could point to is Charm++, mostly because it implements a very popular and useful and good package called NAMD, a molecular dynamics engine. And that is pretty much the only big success you could point to for a long time. And it's a substantial success, but people just weren't flocking to these. And then, in the course of my doing a lot of deep learning stuff, which involves, frameworks, So deep learning is all built around frameworks. If you know anything about neural nets, so deep learning, I'll take a step back and say artificial intelligence, huge part of the field of machine learning has been taken over by deep learning, which is another way of saying neural nets for all practical purposes. And deep learning has become dependent upon packages that do all of the dirty number crunching, a lot of matrix operations, linear algebra operations basically, which drive deep learning. And nobody wants to write linear algebra routines. Nobody even wants to use the existing linear algebra libraries if somebody can make a nicer interface to them. And so people have done exactly that with these frameworks that are very well known in the field, like Caffe or TensorFlow or PyTorch. And they give people these high-level approaches where I can sit in my Python shell and just kind of glue pieces together, if you will. It's a little bit of a simplification. But this is pretty much the way the field works. And in the process of doing a lot of this stuff, I've been involved in it for a good while. And one day I woke up and realized that, hey, these are frameworks here that are wildly successful, that are doing parallel computing, because all this stuff is parallel computing. All the linear algebra operations that you do in deep learning are, to make them effective, they're very parallel. So all that stuff is taken care of behind the scenes. People have written nice parallel programming frameworks that do the linear algebra operations, and you bring in your science, you bring in your architecture of your neural net and construct it at the top level. So frameworks have achieved a great degree of success if we consider deep learning frameworks to be those, and there's no reason you wouldn't, although nobody does talk of them that way, including myself. But nevertheless, there are frameworks that are meant to be more generic in terms of science out there, and Charm++ is a good example if you're looking for one. Hybrid coding, mixing and matching these things, I've already mentioned several times that this stuff works really, really well in mixed and match modes. So for example, if you look at these big supercomputers that have accelerators plugged into them, we've noted that some of the biggest machines, probably half the machines in the top 10, have accelerators, GPUs built into them. If you learn how to use GPUs, you can use your MPI to connect all of those nodes together, and the two combine in a very, very natural way. They're meant to dovetail with each other, and they do. So that should be reassuring to you, but you still have to acquire that knowledge of how to use OpenACC or OpenMP or something else to mix and match them. One interesting thing when you do that is that you'll find that codes which can do both OpenMP and MPI modes, people write these, or they come about in such a way that you assume that if I've got a code that's got, say, OpenMP to use multiple cores, and I've then added MPI to it so that I can use multiple nodes, then of course the best possible way to use that model would be if I've got a machine with 100, I bought 100 of these workstations that are sitting there on the floor. Each one of those workstations has a 28-core node. And so the way, or 28-core processor, I should say, on the node. The way that I would, of course, use this, it seems, would be I'd use MPI, 100 MPI ranks, and each one of those ranks then would be running an OpenMP program to use those 28 cores, because the OpenMP is good at multi-core, and the MPI is good at the message passing to combine them together. That clearly would be the preferred model, right? Turns out that once you write programs like that, it's usually very easy to dial things back and forth, and instead, it's very easy to typically run that code in a mode where instead of being 100 28-core processors, you would just instead run 2,800 PEs. Let's forget the OpenMP part of this code and just run it as 2,800 PEs, right? Which would be how you'd write it right now anyway if you don't know OpenMP, right? You just have no choice, but you'd make it all MPI and you just run it as 2,800 PEs across your 100 boxes, each with 28 cores, right? And you go, okay, that's how I do it as a pure MPI programmer, but that's not going to be as good as that hybrid code. And after you time it, you might be surprised to find that the pure MPI version runs faster than the fancy hybrid version with OpenMP in there. And that's not only, it's intuitively maybe a little bit surprising, but it wouldn't surprise me at all. As a matter of fact, that would almost be my expectation. And the reason is that MPI to each core on a processor actually brings a benefit that OpenMP doesn't, and that's that you've put the effort into domain decomposition to break your code, your weather map up into all these pieces. What you've done is you've also helped a feature of the hardware that's very important these days, the caching. The fact that behind the scenes, the stuff that we hope lives at the compiler and hardware level we don't worry about so much, the caching, the fact that memory locality of data is important, you help that typically by doing the domain decomposition. The OpenMP programmer doesn't have to worry about that, but he also doesn't do anything to help that. He just hopes that the compiler and the hardware do their best. You, in the process of breaking your problem up to pieces and isolating the data into individual pieces, you very often are doing something similar to when somebody tries to help optimize the cache. So the pure MPI codes often run faster than the hybrid codes where somebody has put the effort in to actually write the multi-threaded version on each node. So that's a not uncommon phenomena that catches people off guard when they first see it. Okay. Discussed this already. I've mentioned that data movement is becoming a huge issue in computing. MPI, you can see you're in charge of your data movement, so it's something that gives you a unique handle up on that. But here's kind of a summation of everything we've done so far, so that you can kind of take a step back and understand the process of writing an MPI program and how it varies from anything else. In MPI, in any parallel programming, you've got to spread something out amongst your cores, your nodes, whatever you've got, the cores on your GPU, whatever. And we can see with MPI we're spreading out our data. We're doing a data decomposition. With these other approaches that I talked about here briefly, you're spreading out, and we haven't dived into them enough for you to appreciate it, but you're spreading out things like the loops, the iterations of a loop with something like threading. So we're spreading out other things and other approaches, but with MPI we're spreading out our data. We're breaking our weather map into a bunch of spaces. So that's what we've got to do. And when we do that with MPI, we need to worry about load balancing things. It's the one thing we haven't had to worry about with Laplace code because our approach is so simple, but we do have to worry about it with real codes. We can see with our weather map code, if we did the obvious thing I've been throwing at you so far, each state gets a processor, that we would probably have a load imbalance. We definitely have a load imbalance, right? Some processor responsible for Texas has a lot more work than a processor responsible for New Jersey. And so our weather program is to spend all of its time waiting for Texas or Alaska. Alaska's not in my picture here, but waiting for Texas to catch up. And you have a lot of wasted idle time with the processors for smaller parts of the map. So we'd be silly to do a domain decomposition like this. Instead, we'd really probably at first approach want to break up the map by square miles, an even amount of square miles for each processor. And then if we got fancier, we might want to break the map up to where the weather is more complicated along the coasts. Maybe have more processors there per square mile. And then we might even get fanciest, like real modern weather models would be, and have something that's dynamic and recognizes that a hurricane's creeping up the coast. And so we need more compute power here, and it better change hour by hour as the map evolves. Our domain decomposition would actually evolve. It'd be a adaptive dynamic mesh kind of situation. So domain decomposition is the one area that we've, for obvious time reasons, given short shrift to here. But you'll want to anticipate that as you jump into your problems. Make sure you understand the domain decomposition you're going to use, because it has not only performance implications, but it's the one thing, it's a foundational thing in writing your code that's hard to back out of and change later on. I think I mentioned it before, I'll mention it again, that that's the number one thing that leads somebody down a dead end, a blind alley that can be painful. So pay attention to domain decomposition. You're lucky in that at this state of MPI and parallel programming, you have a lot of work that's gone before you that you could probably leverage. You can probably find a problem similar to what you're doing that gives you some good guidance on which direction you should be heading. At the very least, if you have doubts, there are people you can talk to that can give you some guidance. But the domain decomposition is where parallelization gets made or broken with MPI. Okay, we've talked about some of these hints here, so I won't bother summing it up there. These are all things we've talked about, but I will say this picture now, I hope, is starting to make more and more sense to you here. That you start out, you've got your, a node of your cluster or your laptop in front of you, and you can program it with OpenMP. You can plug in GPUs and program that with some approach, but it's MPI that allows us to glue all of these things together. And as a consequence, this is the future roadmap of software for anybody that's serious about doing numerical computing. And there's very little dispute about this ranking right here. So if it sounds like I'm editorializing a little bit, I don't apologize for that, because I do have some strong opinions with a lot of experience in this field, but you'd have a hard time finding somebody that would argue with me, and you'll see constant references to the future of programming on all of these big machines and smaller machines as well. You'll see MPI plus X is the term that's used by on a lot of these roadmaps that describe the future of scalable programming. And the X refers to, in most cases, OpenMP and GPU programming. Most people think that's the likely X. But it's always MPI plus X. That's the future. You'll also see these PGAS things we mentioned in here. They're kind of some kind of more advanced data parallel approach mentioned. And again, it's even part of the Fortran standard now, so you'll see those. You'll see attempts, the next generation versions of those have gotten a lot of serious attention. They're well funded now, so there are variations on PGAS, and synchronous PGAS ones, and there are things like X10 or Chapel. So you'll see people mention that that might be a way around MPI in the future, but they've also been around. At this point in time, these are now coming up on 15 years old, and they haven't gained a ton of traction. You'll see people mention frameworks. You'll hear, and the decreasing prevalence of these things in the real world is kind of what I'm suggesting here. And then, of course, the computer science types will always say something like functional programming buys you parallelization for free and blah, blah, blah. And once again, the answer, the reply to anybody's enthusiasm for something that might seem a little experimental to you, or at least dubious, is to say, show me some applications that scale. Show me your Haskell success stories, and then we'll take the discussion on from there. So this is kind of a hierarchy of things as they exist now and are likely to exist in the near future. And you're lucky. You're sitting here at the top. Your MPI knowledge will serve you very well on all of these. So don't hesitate to take what you're doing right now. Go apply it to the applications you're interested in right now, the code that may have motivated you to come here, or codes you're interested in, because you've got the skills to start to develop stuff there, and to leverage the huge community you may only be becoming aware of right now that exists with support. The documentation's out there, the forums, the other programmers that are out there doing this kind of stuff. So please be aggressive in your use of this stuff while it's still fresh before it starts to rust on you. It's always a good time to strike.